All right, let's jump right into this explainer. Imagine waking up tomorrow and finding out that everything, and I mean absolutely everything you thought you knew about the ground beneath your feet and the sky above your head was just fundamentally wrong. That is exactly the magnitude of the paradigm shift we are unpacking today. We're looking at the massive transition from a geocentric, Earth-centered universe to a heliocentric, sun-centered one. It's an incredible story of math, observation, immense scientific courage, and the serious friction that happens when brand new data collides with ancient traditions.
So this really hooks right into the core mystery we're unraveling today, the monumental clash between established common sense and groundbreaking mathematics. I mean, for over a millennium, 1,400 years, looking up at the sky and seeing the sun travel across it was literally all the proof anyone needed to know that the Earth stood perfectly still. But what happens when the mathematical models used to predict those movements stop making sense? What happens when one solitary astronomer decides to run the numbers from a completely different perspective?
Which brings us to Section 1, the geocentric universe, the 1,400-year status quo.
To really grasp this 1,400-year status quo, we have to understand that the Earth-centered universe wasn't just some blind guess. It was deeply sophisticated and supported by the greatest minds of antiquity. It wasn't born out of ignorance at all, but out of rigorous observation and logical deduction based on the physics they had at the time. Right around 150 AD, Claudius Ptolemy wrote the Almagest. This was an incredibly detailed mathematical treatise formalizing the Earth as the stationary center of everything. And it became the absolute authority. But, science didn't just freeze completely. By the 13th and 14th centuries, brilliant Islamic and Persian astronomers at the Mirage Observatory, think of minds like Al-Tusi and Al-Shatir, they started recognizing flaws in Ptolemy's models. They actually developed complex new mathematical techniques to fix them, though they still kept the Earth at the center. It wouldn't be until 1543 that Nicolaus Copernicus would utilize similar math to finally shift the center entirely.
So the crucial point here is how early astronomers used these incredibly complex things called epicycles to make the geocentric model mathematically align with the actual night sky. Here's the deal. If you watch a planet like Mars over many months, it occasionally appears to stop, move backward, and then move forward again. This is a phenomenon we call retrograde motion. Now, since they firmly believed planets moved in perfect circles around the Earth, the absolute only way to explain this weird backward loop was to add circles on top of circles. It was an ingenious, if highly cumbersome, mathematical patch.
Copernicus, though, wasn't just moving the Earth. He was really trying to clean up the messy, ad hoc math of the Ptolemaic system. Ptolemy had introduced something called an equant to make his model work. Basically, it was a mathematical point that forced planets to move at irregular speeds, which completely violated the ancient philosophical rule that heavens must move in perfect, uniform circles. Copernicus absolutely hated the equant. By placing the sun at the center and making the Earth a moving planet, he beautifully explained retrograde motion as simply an optical illusion. It's just caused by the Earth overtaking other planets on the inside track. It was mathematically elegant.
Moving into Section 2, Copernicus moves the Earth. The mathematical disruption.
Enter Nicolaus Copernicus. But remember, he wasn't looking through a telescope. He was poring over ancient texts and complex geometry, looking for a more harmonious mathematical order to the cosmos. And while we casually call his idea the heliocentric model, Copernicus actually placed the sun just slightly off-center, so technically it was a heliostatic system. He kept some of the false Ptolemaic assumptions, like the very rigid belief that planets must move in perfect circular orbits. Because real orbits are actually elliptical, Copernicus still had to use his own series of small epicycles to make his math match the sky. His system was revolutionary for sure, but contrary to popular belief today, it wasn't actually any more accurate at predicting planetary positions than Ptolemy's old model.
To answer the obvious question, why don't we feel the Earth spinning, Copernicus used his brilliant ship analogy directly from his primary text to explain relative motion. Think about the last time you were sitting on a really smooth riding train, and the train next to you started moving. For a split second, you probably felt like you were moving backwards, right? Copernicus reasoned that because the Earth's motion is uniform and we are moving right along with it, the atmosphere, the people, everything, we simply cannot feel the spin. The apparent rotation of the stars is really just the sky passing by our planetary window. Which leads us to Section 3, the scientific pushback, why geocentrism still made sense.
It is absolutely vital to understand that the resistance to Copernicus wasn't just religious dogma. There were highly valid scientific objections at the time. When we look back, we tend to think the people resisting the moving Earth were, foolish. But with the science available in the 16th century, geocentrism was a highly logical position. The brilliant astronomer Tycho Brahe captured the Eris physics problem perfectly. Aristotelian physics had absolutely no explanation for how a massive, heavy Earth could be moving through space. Sir Isaac Newton's laws of gravity were still a whole century away. In their understanding, heavy things fell to the center of the universe, and light, ethereal things, like stars and planets, swirled effortlessly above. The idea that a giant ball of rock and dirt was hurtling through the void at unimaginable speeds, it literally broke every known law of physics.
And this leads us to the stellar parallax problem. Think about it. If the Earth is moving in a massive orbit around the Sun, our vantage point of the stars should change from summer to winter. They should shift slightly in the sky. But astronomers measured meticulously, and the stars didn't move an inch. The only way Copernicus's math worked without this shift was if the stars were so incredibly, impossibly far away that the Earth's orbit was just a tiny speck in comparison. Because stars appeared to have width to the naked eye, Tycho Brahe calculated that if they were really that far away, an average star would have to be vastly larger than our entire solar system. Scientifically, at the time, that seemed completely absurd. No way, right?
Let's look at Section 4. Galileo looks up, the telescopic catalyst.
The entire debate transformed from mathematical philosophy into hard observational science the moment Galileo Galilei pointed his newly improved telescope at the sky in 1609. Suddenly, we aren't just doing math on parchment anymore. We are gathering empirical, physical data that Aristotle and Ptolemy could never have even imagined. These rapid-fire discoveries destroyed the Aristotelian idea of perfect, unchanging heavens and gave us the physical evidence that Copernicus lacked. By finding moons orbiting Jupiter, Galileo proved definitively that there were centers of rotation in the universe other than Earth. By observing Venus go through crescent and full phases, a lot like our moon, he proved mathematically that Venus must be orbiting the Sun, not the Earth. The heavens were no longer these untouchable perfect spheres. They were dynamic, cratered, changing physical bodies. It was a real game changer.
But, as you can imagine, these discoveries caused immense friction. Looking at the Catholic Church's position at the time, articulated here by Cardinal Bellarmine, we see a real fear that abandoning the prevailing scientific consensus without absolute proof was incredibly dangerous. Now, the Church wasn't necessarily anti-math. In fact, they relied heavily on astronomy for calendar reform. Bellarmine told Galileo that treating the moving Earth as a mathematical hypothesis was perfectly fine, but declaring it physical reality contradicted the literal, accepted interpretations of biblical passages. Bellarmine stated that if conclusive physical proof existed, the Church would carefully reinterpret Scripture. But without unassailable proof, which, remember, physics still couldn't provide, changing the world order was viewed as reckless.
Now, Section 5, the Galileo Affair, the climax of the paradigm shift.
What started as an academic debate over telescopes and geometry was about to explode into one of the most famous trials in human history. Galileo had actually enjoyed the patronage of Pope Urban VIII, who encouraged him to write about the two systems impartially. So Galileo published a book called The Dialogue, structuring the debate between three characters. But he disastrously placed the specific arguments of his patron, the Pope, into the mouth of the character named Simplicio, a name which literally translated to simpleton. Meanwhile, Salviati, the Copernican character, routinely humiliated Simplicio with unassailable logic. Whether it was intentional or just incredibly poor judgment, Galileo deeply alienated his most powerful supporter at the absolute worst possible time.
Breaking down the escalation, we see how a breakdown in communication and patronage ultimately led to Galileo's trial and his tragic, lifelong house arrest. Back in 1616, the Inquisition had formally warned Galileo to stop treating Copernicanism as a physical reality. When the Dialogue was published in 1632, clearly championing the moving Earth, church authorities felt he had directly violated that earlier injunction. He was tried in 1633, threatened with torture, forced to publicly recant his findings, and his revolutionary book was banned.
While Galileo probably never actually muttered his famous rebellious phrase, "and yet it moves," after his trial, it perfectly captures the reality that scientific evidence outlives political decrees. Though he was confined to his villa for the rest of his life, his telescopic observations had already let the genie out of the bottle. There was no going back. He spent his final years writing foundational works on physics and motion that would eventually fall into the hands of a young Isaac Newton. And Newton, of course, would finally provide the gravity-based physics needed to prove Copernicus and Galileo completely right.
What you should really take away from this is how paradigm shifts actually happen. They aren't clean and they aren't easy. They require brilliant leaps of math, brand new technology, and a real willingness to challenge the very foundations of human knowledge. So I want to leave you with this final thought.
What foundational beliefs do we hold as totally unquestionable today that might just be waiting for our generation's telescope to shatter them? Keep questioning everything, and we'll see you in the next explainer.